Okay, let's start the afternoon session. So we're delighted to have Adam Wagner from Worcester Polytechnic, who will give the first of two talks by three speakers of the case studies in learning for mathematics.
Yeah, thank you so much, Mike, and thank you everyone for coming. Today I want to tell you about a couple of different ways you can use machine learning in your own research. And I just want to start by saying that Boris gave a really nice talk about the theory of ML, but this is going to be the complete opposite of that. This is going to be a very practical talk. I'm a mathematician. I'm interested in what kind of methods there are that I can actually use to make progress on my own research. So that's going to be the focus of the talk, just very practical. What does it look like when we actually try to use these different machine learning algorithms in practice? So the two methods I will talk to you about is, first I will tell you about the simplest possible thing you can do, just very simple reinforcement learning, and then we'll talk about how we can do these things a little bit smarter. So everything I'm going to say is joint work with many people over the past few years. So Gergely, Jordi, and Francois are all here in the room, and Jordan Allenberg will be here next week when I don't think he's going to join. Okay, so let's begin. I will start by telling you the simplest possible way you can go about attacking conjectures in mathematics using reinforcement learning. And to set the scene, the idea is as follows. We have these companies, for example, DeepMind was mentioned many times in this conference already. And these companies have come up with reinforcement learning algorithms that are very good at playing chess, Go, Atari games, and they can play these games at superhuman levels. And the real interesting thing about all these programs is that they start by knowing absolutely nothing about the games at all, only the rules, and they figure out everything else just by playing the games many times, just by themselves. So given how successful these algorithms have been, how nice would it be if we could use them in mathematics as well? And you can kind of imagine how we could do that. Instead of inputting the rules of chess, you could take a problem in mathematics, phrase it as a game, and input this problem into the reinforcement learning program. So, for example, you could start with the problem, how many edges can a graph have if it doesn't have any triangles or four cycles? You can phrase it as a game by saying you have a player, you start offering edges to the player one by one. For each edge, the player can decide whether they want to take this edge or not take this edge. And at the end, you give a reward reflecting how well they did in this game. And the idea is that you phrase this problem as a game, you do a program, go away for a few days, and when you come back, you find an algorithm or a program that's very good at constructing graphs with finding edges and no cycles of 0.4. So that's the basic idea. And the reason this would be good is that if this algorithm works, if this method works, then this would give a very general approach we can take to attack any problem that could potentially have a counterexample using this way. So that's what we're going to try to do here today. We are going to take problems in mathematics, conjectures, we're going to phrase them with games, and try to tell the reinforcement learning algorithm that please try to get good at the game of finding counterexamples to this conjecture.
The more edges, the better.
Yeah, so in this problem, the more edges, the better. So in this particular game, we could evaluate how well the player is doing by giving a reward function that could be something like you get 1 point for each edge you included, and you get some kind of penalty of 100 points if you included a cycle of 0.4. And then you want to maximize this score. Right, so that's the idea. We are going to try to take open conjectures and use this method to find counterexamples to them. Now, this goal is still very vague, very wishy-washy, so let's be more precise. In this experiment that I will first present to you, we're going to try to do everything without using any human insights at all. So I want to see how well these methods can do if we just leave everything to themselves and we don't give them any help at all. If you decide on this axiom, this is going to force your hands in a couple of different ways. In particular, you're going to be looking for a general setup. You won't be allowed to change the architecture of the neural networks, for example, or change the hyperparameters between different applications, because that could be kind of a way to cheat, to insert some human insights. So what we're going to be after is one generic, simple baseline learning algorithm that we can then throw at 100 open problems and just see what happens. So this is going to be the first experiment we're going to look at. And as I said, it's going to be a very practical talk. So let's look at what it actually looks like if you try to do this in practice. So let's start with this example here. First example is just a baby example. Here's a conjecture from literature that we know is false. So we should be able to find a counterexample with our method as well. So this conjecture says something about graphs. It says that for every graph, the sum of the largest eigenvalue and the measuring number is at least some kind of function of the number of vertices. But I would like to ask all of you to try to forget everything about what you know about graphs, and let's completely ignore what eigenvalues and measuring numbers are. Let's focus only on how we would go about approaching this conjecture if we didn't know anything about graph theory at all, and we only wanted to use reinforcement learning without any smart ideas. Well, if you want to get started, we have to decide on two things. We have to decide how we are going to phrase this problem as a game and what the reward function for this game should be. Well, phrasing it as a game is very simple. We can just generate the graph edge by edge. And what should the reward function be? Well, we want to minimize lambda 1 plus mu. So we can just take the reward to be lambda 1 plus mu of the final construction. And minimizing this reward is the same as maximizing minus lambda minus mu. So this is the simplest things we have to decide to get started with this method. Then we plug it into our favorite learning algorithm for our chosen value of n. We go away on a holiday, and when we come back, we will see something like this. So in this baby example, the blue line represents the score that the program is able to achieve. You can see that eventually, as time passes, this blue line slowly went below this orange dotted line. And since the orange dotted line represents the right-hand side of this inequality, this simply means that at this point, I managed to find a counterexample to the conjecture. And now we are very happy. If this happens, then this was a dream scenario. We did the simplest possible thing that we could, and it worked. There's not much to talk about. I can already tell you right away, in the overwhelming majority of the cases, this is not going to happen. Things will go wrong.
Are you going to tell us what reinforcement learning algorithm you use?
I wasn't planning to. I can say that if you're planning to do this approach that I just described, where you want to throw it at 100 different problems, then you're looking for something that's very stable, where it doesn't really matter whether you choose the right hyperparameters or you
We're
choose.
curious which one they use for your experiment.
Yeah, so it's a cross-entrop method. It's a very, very simple, very stable method. I'm very happy to talk more about it, but in the second half of the talk, I will tell you about a much better method.
Yeah.
So I'm going to focus on that, I think. I want to start with this method because it's really, really simple. But then the conclusion of this part of the talk will be that this method is not very good. Yeah.
So this example is for n equals 19, I guess, because and so the previously known counterexample was with n equals 600,
yeah.
Right? So you found something in 19, it just went from n equals 1 to 19, and it,
yeah. So you just try a certain big value of n. Previous known counterexample was 600. Probably people didn't try to improve it so much, so it's not really a important result to improve the 600. Yeah.
And is training this for n equals 19 related to training it for n equals 20, or is just each n you start over?
Good question. I have never found a good way in practice to transfer your knowledge from 19 to 20 and so on. I would just start retraining, and this really bothers me because there should be a good way to do it. In practice, I could never find a good way to do it, unfortunately. Okay, any more questions?
So just for clarification, n is a fixed,
Yes.
and
N is
each
fixed.
iteration you add, you try to add or remove an edge. That's the iteration.
Exactly. That's correct.
Thank you.
Yes, everything is for one fixed value of n here. If you don't find a counterexample for n equals 19, you can try n equals 23, n equals 30, and at some point you give up.
Try a game where the moves include adding vertices. So
We did play a lot with these kind of things where you can add vertices, and it just never worked very well. So
But at some point, it's in some sense sort of the problem is this one search, and now that you've reached it, sort of you throw away you don't need a trained product, you just sort of
exactly. So
you're just interested in having the thing and then you throw it away.
exactly.
So
So
one thing you could try to do is of course sort of you could try to, as of course, going from 90 to 20 changes the action space, it makes it larger, but going from 90 to 80 makes it small. So you could sort of see whether this is trained agent with 90, maybe you can find contact something with 80.
Maybe. I suspect that the counterexample with 18 might look. I mean, if it looks similar to the one with 19, then yeah, that.
What is state space? State, the action space, I understand. I'm interested in the state space. If we go out, we probably see that we take the state.
Yeah, I assume it's this. I mean, yeah, I would have assumed it's a graph with the edges there.
The full graph, so you state space dimensionality is very much.
Okay.
There's no compression of the state.
I see your graph, there's lots of little wiggles where it goes up, the loss function goes up.
Yeah.
Does that mean you use some kind of metropolis algorithm, the temperature, to occasionally accept a transition which increases the loss function?
No, so that's
Then why do those little bumps go in the y-axis?
there are always bumps. It doesn't always decrease. It take us.
So I'm just asking, what's the rule for accepting or rejecting an edge above? You accepted the edge lower the loss function.
No. That's not how the algorithm works. I have to remember how. Yeah.
So every iteration is a sample of a lot of graphs. So each one of those x-axis is like sample many graphs and take the top 10% and then update some probabilities. And so, you know, those little fluctuations are like a particular sample graph. Like a particular batch, you just got unlucky and you got a couple of graphs that were worse than the previous graph.
Okay. But why is that overall roughly monotone increase in trend?
It's roughly monotone because it's smoothened. I suspect there are many more wiggles here that I just smoothened out by averaging out the curve a bit more. But eventually we expect.
I don't understand what's being learned. What's the network?
What is the objective function?
It's the average.
Okay. So what we are doing is we have a network. Initially, it's completely random, and we use it to generate a graph probabilistically. How do we do that? First, we input the empty graph and a pointer to the first edge, and it outputs a probability on what it thinks should be the probability of taking the first edge. And we sample according to the probability, and we end up either taking the first edge or not. Then we plug in this graph that we have now with a pointer to the second edge. Now we again get a probability. We sample the second edge according to this probability, and now we end up with a new graph. And we keep repeating it until we've sampled each edge. So this way, one particular network gives us a probability distribution over the set of all the graphs. And once we've done this 1,000 times, we sample 1,000 graphs from it. Now we are going to change our network so that in the next generation, it will output better graphs and more likely. So we are going to evolve this probability distribution over the graphs. How do we do that? We take the best graphs that we've created in the previous generation, and we pretend that in the best 10% of the graphs that we created, we made all the correct decisions. So we are going to make it more likely that in the next generation, we are going to output graphs that are more similar to the top 10% of the previous generation by shifting the weights of the neural network a tiny bit in the right direction. So it's always going to be a probabilistic algorithm. There's always going to be wiggles. It also depends on what are the 1,000 graphs that we randomly sampled from everything. But we always fit the neural network to the best 10% of the graphs that we sampled in the previous generation. And we hope that this will eventually lead to very good constructions. Sometimes it does, usually it doesn't.
Your final answer looks very close to that conjecture square root of n minus 1 plus 1. If you take the minima and you plot them, do you get something with the square root and you can fit a curve that's even better?
I'm not trying to understand the question, sorry. Can you repeat that?
Well, I mean, you're close to the bound, right? If you shifted the orange line down a little, it would satisfy it.
Yeah.
So there's something non-trivial about this bound, right? So if you just look at the minimum there, you have it from n to 1 to 100. You can just look at what you find. and see what the bound should be.
Yeah.
It's square 19 minus 2 plus 1.
Yeah, absolutely. I mean, once you move through to the conjecture, you can think about what the conjecture should have been. And there was a reason why this was the conjecture, but it's obviously false. So the motivation for it was incorrect.
Was there any modification of this conjecture? True?
I-
Just over.
But I'm saying, even if you don't know what the conjectured functional form is, you could determine it from your results you already have by just plotting them and doing
You could.
regression.
Absolutely. You can come up with a new conjecture, that's fine. I don't know if there is something interesting. But you can definitely come up with a new conjecture just by looking at the best construction you find and take it from there. Yeah,
Okay, you talked about like starting by feeding in the empty graph and.
Yeah.
And asking about this edge and
Yeah.
then some later stage, is that all being fed into the same neural network?
Yeah.
Okay. So part of that input is like, which edges are already there, and then which edge are we thinking about?
exactly. So two inputs, the current graph and the pointer to the edge that we're currently considering. Yes. Okay. So what I wanted to say is that this is really a dream scenario. We tried our really simple learning algorithm, and if just quickly find a counterexample, and if this happens, we can look at the counterexample. Happens to be something very, very simple. And we can also look at how the best constructions evolved over time. Initially, we had no idea what we were doing. We were just generating random graphs. Very quickly realized that sparse graphs are the way to go. And eventually this kind of balanced double star structure has emerged. But as I said, this is really a dream scenario. You plugged in the easiest possible way to phrase the problem as a game. You plugged in an obvious reward function, and it found a counterexample. This never happens. So what I want to do here is I want to look at a couple more examples just to show you what are some things that can go wrong and what are some different aspects of this method that are useful to keep in mind in practice. Okay, so let's immediately jump to a second example that's very, very similar to the previous baby example, but things will behave very differently here. So here is a conjecture. It says that any graph, the sum of the proximity and some kind of distance eigenvalue is always positive. Once again, I ask all of you completely ignore, please, what proximity and distance eigenvalues are. It's not important. Let's focus only on the reinforcement learning aspect of it. How are we going to attack this with RL? We need to do two things. We need to decide how to phrase it to the game. Well, that can be the same thing. We just generate graphs edge by edge. And we need to decide what the reward function should be. And what should the reward function be? Well, previously it was lambda 1 plus mu. Only thing we need to change is change lambda 1 plus mu to pi plus delta. Otherwise, we can use the exact same setup that we had before. You pick your frame rate value of n, you plug it in, and when you come back from a holiday a few days later, you find this graph. So this is the best construction your method was able to find after a couple of days of learning. Now, the value of pi plus delta for this particular graph is something like 0.4, but the conjecture was that pi plus delta is always positive. So the fact that here it's 0.4 simply means that in this example, the reinforcement learning algorithm wasn't able to find a counterexample of the conjecture for n equals 30. So this is by far the most common thing that happens. You plug in your problem to the RL algorithm, it tries its best, but it doesn't find a counterexample. Now the good thing is that this happens very often, but many times it still gives you some really valuable information. For example, if you take this graph and you put it on a tray and you take it to any undergraduate mathematician, it will be completely obvious what kind of graphs you would want to try if you want to find counterexamples of the conjecture. Because you just start playing around with this flower, you increase the number of petals, you make the sticks longer and shorter. It turns out if you start playing around with these things, there's no way you will not eventually stumble upon a counterexample, because already something like this happens to refute the conjecture. So this is a common example where RL doesn't find a counterexample by itself, but it gives us some help so that a human can just take over and finish the job using our own intuition. Okay, what else? Well, this method has absolutely nothing to do with graphs. I'm a graph theorist. Most conjectures I know about are about graphs, but really any problem that's
We're
about.
going to come back to graphs. I mean, out of your 100, how many fell into this?
the category where it didn't find a counterexample.
But it gave you, you could use it to make a counterexample.
So it didn't find a counterexample in like 95% of the time, and it always gives you some kind of insight, but usually it's not
Quite
quite
insight that led to a counter.
rarely.
This was also
5%, I would say. Okay. Small number. Most of the time you try it and you don't get anything. I would say 90% of problems I tried with this method, nothing came out of it. Okay, so
Can I ask? Sorry.
yes,
Go back to the thing that motivated this conference.
Yeah.
How did you know to draw it in this way? Like somehow the main information, like if you just gave me this adjacency matrix, I would have said, right, but you drew it in this way and you suggest there's a flower and there's legs, so you had to input something that you knew about graph theory to realize that this is the representation.
so this was drawn by one of the standard NumPy draw graph functions. I don't know which one.
No, but nonetheless, that knows something about how a human wants to see a graph, right?
I think it just minimizes some kind of energy function. I don't know exactly how it works,
But somehow that tells you that that energy function is somehow related to this conjecture. Right, I mean, like, that's what it seems to be saying.
it helps if you can draw the graph in a way where a human can look at it and then we can start spotting some stuff. That's when the graph is sparse enough, then it probably doesn't matter how exactly you plot, as long as it's something reasonable, you will be able to see that there's a flower going on here. If it's a dense graph, then looking at it won't really help, and I wouldn't be able to spot it like this. Yeah. But how to automate this process? That's a really interesting question, and I have no idea how to do this. For example,
For a different conjecture, right? You might come up with something you can't exactly. If you had a better way of visualizing, you know.
Absolutely, and there are definitely conjectures like this.
That's what we're talking on. Of course, the idea of putting the chance,
Yeah, percent.
very chances, but these have, whatever you put it.
I don't know, I think if you randomly arrange the vertices on the.
Only one vertex is high variance.
Yeah, you cannot miss this one.
I mean, these graph drawing items are pretty simple.
Yeah,
This particular.
yeah, maybe this, that's a good point.
Grzegorz, did you have a question?
I wanted to remark that this algorithm, more or less what this does, I think we're using the same package, which I forgot how it's called, but as far as I remember, this algorithm more or less is like places negative charges everywhere and they just try to spread it far.
Yeah.
So it just happens so to be aligned with this problem, but we work on something else with Adam where there are also graphs, and actually I had to write custom way of embedding graphs because this default thing was actually doing the very opposite. It was blurring everything you wanted to see, so. It just happens so to be aligned with this particular problem.
Did you want to say something?
No.
All right. So just very quickly, a few more examples. I want to spend more time on the more interesting part of the book, where we actually improve this method. I just want to quickly say that this method has nothing to do with graphs. Any problem that can be phrased as a finite sequence of finite decisions could in theory be attacked the exact same way. So here's the question. How large could a permanent 0-1 matrix be if you assume it doesn't contain a 3-1-2 pattern of ones? So here, white squares denote zeros, dark squares denote ones, and the kind of stuff you're not allowed to have is you're not allowed to have 3 ones in this particular configuration. Question is, how large can the permanent of such a matrix be? So this was a question of Brody and so they had a guess. They said the best thing to do is the simplest possible thing. Take 3 main diagonals and the leftmost column. You can check that this doesn't contain any of these forbidden 3-1-2 patterns, and you can believe me that the permanent of this matrix is some kind of Fibonacci number, -1, comes out of the recursion. Okay, how do we attack this with RL? Well, we can phrase it as a game by going entry by entry, deciding to put a 0 or 1. What should the reward function be? Well, now it's suddenly not so obvious anymore, and for most problems, it's not obvious. There's multiple reasonable reward functions that we can choose. Here, the reward functions should be something with a permanent that we want to maximize, and it should take into account that we shouldn't have any of these 3-1-2s. So to me, one natural thing to do would be a reward function, which is the permanent resulting matrix minus some kind of penalty function that takes into account how many of these forbidden 3-1-2s we have in the final construction. And if you do it this way, that's definitely not the only way to do it. If you do it this way, you just have to make sure that the penalty is big enough. Otherwise, the network might learn that it's beneficial to include some of these forbidden copies because the gain you get in the permanent outweighs the loss you get in this penalty function. And then you end up solving a different problem. As long as you don't do this problem, this works. And it turns out the best constructions are something very, very different from what was in the conjecture. And you also have this really funny initial sequence of numbers where it starts out with powers of 2s that breaks down only at n equals 8 for some bizarre reason that I don't know anything about. Okay. Now, there are some problems where I can clearly say that this method is not the right thing to use. In particular, if the reward function is something really complicated that consists of multiple very different components, that's an example of a problem where I would definitely not use this method because in my experience, it doesn't work very well. Unfortunately, this is what happens in most complicated and most interesting conjectures. So let's have an example of this sort as well. Here's a question of Wagner and Reinhardt. They asked, do there exist 2 graphs so that they have the same distant Laplacian spectrum? One of them has a rare regularity property, the other one doesn't have this rare regularity property. Okay, so imagine we set it up as a game, we constructed 2 graphs, and now we would like to cook up a reward function that measures how close this pair of graphs is to satisfying the properties of the conjecture. How would we cook up a reward function like this? And now things become tricky. Because the reward function probably would have these 3 components. A natural way to do it would be to have a component that measures how close the distant Laplacian spectra are to each other. Would have a second component that measures whether or how close G is to having this rare regularity property, and maybe a penalty function that gives a penalty if H happens to also have this kind of regularity property. So now what we have is a reward function that has 3 completely different components that try to teach the 3 different things at the same time to the network. My experience is that in these situations, this method is just terrible. I would definitely not recommend using it. In this particular example, I managed to make it work, but likely other methods would have been much better at this. It turns out these 2 graphs have the same characteristic polynomial, and they have the properties of the previous question, but it was really, really painful to get the learning to work in this case. Okay, and just one more example. What about infinite conjectures? Most interesting conjectures are about what happens asymptotically when something goes to infinity. So can we attack these problems with this method? Usually it's very hard, but occasionally there are ways to do that. So here's an example. This is the conjecture of Erdős. He said, take a graph, count the number of 4 tuples of vertices that are all connected to each other by an edge, count the number of 4 tuples of vertices so that no 2 of them are connected to each other by an edge, add up these 2 numbers. And he conjectured that this sum is asymptotically minimized by random graphs. So this conjecture was open for about 27 years until a breakthrough result by Andrew Thomason, who showed that this is false. And he gave a beautiful explanation to why this conjecture has to be false. Now, together with Ben Jury, who's a really smart computer science professor in Belgium, we wanted to disprove this conjecture using our reinforcement learning, and we found a way to do that. So how can you attack such infinite conjectures using any kind of computer search? Well, in my opinion, there are 2 main methods. First, you can ignore the infinite parts, and you just pick one large value of n, try to find the best construction for that large value of n, and hope that you get enough insight from it so that you can take over and understand the structure and just hook up an infinite sequence of graph that is going to be a counterexample to conjecture. We tried it for this problem, but unfortunately for these kind of conjectures, the best graphs are some kind of algebraic constructions that are really, really hard to generalize just by looking at one particular example and just doing it by hand. So when we tried it, we found some really good constructions for n equals 50, 60, 70, and we had absolutely no idea how to generalize them. So if this doesn't work, then you're left with the second method, somehow trying to find a stronger conjecture that's about finite graphs. So somehow reduce this asymptotic conjecture to a finite conjecture. And luckily in mathematics, we do have many, many tricks like this. In this particular case, something called blowing up a graph works very well. So this just means that instead of constructing an infinite sequence of graphs by computer, which would be possible to do, we are just going to construct one particular graph, and we are going to hope that the sequence of blowups, which is direct products of this graph, the complete graph of vertices, is going to be a counterexample if you let m go to infinity. Once you write this down, you have to think about what does this sentence actually mean. It turns out that you want this limit object whose value only depends on properties of the graph G and not on M. You want this limit object to be below a certain value. And once you realize that, that just means that you can take this particular limit object, you can use this as your reward function, and everything else is going to be the same as before. You pick your favorite value of M, you plug it into the learning algorithm, and if you've done everything well, you end up finding a counterexample to conjecture. Now, to me, this has a good and bad message to it. Good message is that this really shows that if Erdős had made this conjecture today, then it wouldn't have been open for 27 years. With this method and other methods, we can easily refute conjectures that were impossible a few decades ago. The downside is also highlighted here. So far, I've always showed you the counterexample we found. In this case, this is the counterexample, and this is an example where drawing the graph doesn't help at all. I have absolutely no idea what this graph is. I gained zero insight from looking at this graph. Whereas if you read the paper by Thomason, you actually end up understanding why this conjecture is false. So there's really no doubt that this paper has much more value to it than just a simple counterexample. It really just gives you this one bit of information that the conjecture is false. Okay, so let me just, yeah.
Did the idea of blowing up to km come from that paper?
Yeah, it did, yeah. It's a very standard idea in graph theory, and we expected it to work. So that was a good hint, absolutely. The counterexample is smaller, but in the end, it's very clear that the Thomason paper is just much, much more value to mathematics than just having this kind of counterexample like this. Okay. So
Did the counterexample follow the logic of the Thomason paper, or did it sort of?
I mean, we knew that blowups are likely to lead to counterexamples, but this graph was constructed with RL.
So even in hindsight, knowing sort of the argument Thomason gave for why this conjecture is false, looking at this graph is look up.
Absolutely no, it's just some graph. Yeah. That's all I can say about it. Okay, what are the advantages and disadvantages of this method, in my opinion? This is completely just an opinion. To me, the advantages is, well, first of all, it's a really fun thing to do. It's really addictive to plug in a problem and just watch it learn and construct better and better constructions, and it's really, really fun. And even better, occasionally it does work. So I just showed you a couple examples where it worked very well. But I didn't show you the 100 other examples where it didn't work at all. So overwhelming majority of the times, you try this, it's not going to help you at all. So reinforcement learning is very, very slow, it doesn't scale well, and many times it doesn't even outperform much, much simpler methods. So reinforcement learning is not magic, and just because you can attack a problem with RL doesn't mean that you should. Having said that, there was recently a really interesting paper where this group of authors realized that this particular method that I just described works very well on a tiny, tiny subset of graph theory. They tried very specific types of algebraic graph theory conjectures. They found a list of 68 conjectures, and they managed to refute half of them. I mean, this probably says a lot more about the quality of the conjectures than the method itself. All right.
Did you consider making like some sort of benchmark for the data set?
This needs to be done, and I really meant to be doing it for years, but I haven't yet. Yeah, absolutely. Benchmarks would be super useful in any such things. Okay. So far I presented to you one really simple method. Let's talk about how we could do better than that. And with Hamza, Jordan, and Jordi, we were thinking about what are the issues of this method, how can we improve that? And the one thing we noticed is that amongst the many other issues with the previous method, one issue is that we construct graphs edge by edge. And of course, if a human draws a graph, we would never ever do that. We would have some global picture in mind, and we would draw some global idea, and then we would fix things locally. So a human would never just draw a graph edge by edge, create a matrix entry by entry. We would have reasonings at multiple different levels. So we wanted to take a step towards an algorithm that's more local and also global at the same time. Of course, this is not a new idea, but we wanted to come up with an algorithm that actually works well in practice, that we can use to attack more problems that we were interested in. So let me show you the algorithm, and I'm going to motivate it with one particular really nice problem. So here's a question. For a long time, we thought it was a question of Jordan Ellenberg, but as is often the case in combinatorics, a year or two later, we realized that Erdős had already asked this a few decades ago. So this question is a really beautiful question. The question is, you have the n by n grid. You want to place as many points on this grid as possible. And only rule is you're never allowed to have 3 points that satisfy that the distance between the first two is equal to the distance between the second two. In other words, you're not allowed to create an isosceles triangle, so a triangle with two sides being equal. Question is, how many points can you put on the grid like this? So let's go to maximum f of n. Let's first start by doing mathematics. Maybe we can solve the question without doing any computer search. If you know some probabilistic combinatorics, then a lower bound of n over root log n is very simple. I give it as a homework question to my students, and they were not happy about it, but they could have solved it in theory. And if you are willing to do something a bit more technical, you can get a lower bound of constant times n. So standard thing and combinatorics that you can get rid of this root log n term that you get from iteration if you do something more technical. It's not easy, but it's been done. You just have to follow the recipe and you get a linear lower bound. So f of n is at least linear. That's the best lower bound that's known. What about upper bounds? Well, you definitely cannot choose more than n squared points because that's how many points you have on the grid. And you can improve this by another tiny factor by realizing that a horizontal line must contain points that do not contain a 3-term arithmetic progression because that's forbidden. Then you can use some deep theorems about the density of sets that do not contain 3-term arithmetic progressions. The best upper bound is a factor of this kind of form right now. So you get a slight improvement from this n squared term. And that's the best thing that's known. In particular, proving that f1 is bounded by n to 1.99 is still completely open. And to me, this feels really embarrassing. If there's such a huge gap between lower and upper bound, it's a factor of n lower and upper difference. I feel like I should be able to improve these things, but I tried very hard. Other people also tried very hard. And we have no idea how to improve either of these two bounds. Seems like a hard problem. Okay, if we cannot do it mathematically, let's try to at least use computers to come up with a guess about what the correct answer should be. Okay, well, how do we do this? Well, use computers to find the best constructions for small values of n. Up to n equals 7, you can do it by hand. These are the best constructions. You can check that there is no isosceles triangles anywhere. For slightly larger values of n, there's a question or no, sorry. For slightly very larger values of n, you have to use computers probably. LP solvers or maybe very different methods also work. Up until 10, these are the best constructions. Turns out the best standard method to use are set solvers for this problem. they work up to roughly n equals 30-ish. So for 16, we have two very, very different looking optimal constructions. For 27, you have this butterfly, but you also have this kind of construction that's very different. And for 32, this is probably the best construction, but this is the point where SAT solvers start breaking down. Within a reasonable time of compute, we were not able to find a proof of equality here anymore. So this is the point where we start giving up hope that we get proofs of optimality after this. Okay, so first of all, is this function linear or quadratic? Well, let's plot them and let's put a line through some of these points. This function is definitely not a quadratic function. It looks suspiciously like some kind of linear function. And if you're willing to be even more brave, you can even look at the slope of this line, and it looks like the slope is 16/9. So maybe, just maybe, this function is something like 16/9n, or maybe we are just a bit too optimistic about from this previous picture. If this function is linear, then since the function value of 16 was 28, value of 32 was 56, it means that for 64, we expect the answer to be roughly 112-ish. So now we have a guess about what the answer should be for 64. Let's see if we can actually find this. So we tried really, really hard. We're hoping at this point that maybe if you could find the best construction for 64, then we could spot what the pattern is and we could generalize maybe. In retrospect, we're probably a bit naive at this point. But we tried very hard to find this 112. We tried all standard methods we had at our disposal. And after a couple months, I think 3 months of trying, the best we could find was 108. So here's the construction with 108 points on the 64/64 grid. Okay, what now? We tried standard methods, it didn't work. But there's clearly some kind of pattern going on here. If there's a pattern going on here that we don't understand, maybe some kind of machine learning tricks could be a little bit helpful. That was our idea, and that's why we started going down this road. So here's what we did. Over these 3 months where we tried all of our heuristic algorithms, we saved all the best constructions we've seen throughout this time. So we ended up with a huge database of about 1 million constructions, which had between 104 and 108 points in them. We had this big database, and we gave this big database to a transformer. We used a very simple implementation of transformer called Wagner that's available online, and I really recommend using it because it comes with a nice tutorial video, so I can actually understand what's going on in it, and it's a very, very simple implementation that's easy to modify. So you take this big database of lots and lots of good constructions, you show it to the transformer, and then you tell the transformer, pretty please give me more constructions like the ones I just showed you. So how nice would it be that after we train a transformer on these constructions and ask it to give us more constructions, eventually it would give us, by accident, some constructions that are even better than the ones we had in the training set. So that's what I hope. Maybe if you just generate 1 million new constructions, some of them will have 109, 110, or maybe even more points in them. Unfortunately, that's not how things work. If you show a transformer lots and lots of constructions with 108 points and ask it to generate more examples like in the dataset, it will give you more constructions with 108 points. So this was very naive and it didn't work at all. The model gave us lots and lots of new constructions with the same number of points in them as in the training set. So this didn't work. What now? Well, initially we were stuck because it didn't improve, but then we noticed something fun happening. And the fun thing was that once the training set was big enough, once we had enough good constructions in the training set, what we noticed is that the transformers was outputting new constructions with 108 points at a much, much faster rate than we were able to find with our standard methods. So initially, when we only had a couple good constructions, that wasn't the case. Then eventually it started outputting, once the database was bigger, it started outputting 108 at a faster rate. And once we crossed some kind of threshold, the rate at which it was outputting new good constructions was significantly faster than we could find them with the standard methods. So after we crossed some kind of threshold, this method was giving us new constructions at a significantly faster rate than before. Okay, but this is still only 108. So what good is this? Well, next step is the following. If you believe that 108 is not the solution to this problem, then in this huge search space, somewhere there exists some 109s, some 110s, and so on. And because the scoring function is very smooth, these 109s must be surrounded by lots and lots of 108s. So this means that some tiny fraction of the 108s must not even be locally optimal. So how about we take every single output of the transformer and we launch a tiny, tiny, very, very silly local search from all of these and see if we can just improve one of them by virtue of them not even being locally optimal. That was our idea. We tried it and it immediately went up to 110 after us being stuck on 108 for about 3 months. And we have found lots and lots and lots of 110s and never anything better. So in like 1 hour, it went up to 110, and for 2 weeks after that, never moved. I still think that 112 is possible, but who knows? This is the best one I could find so far.
Question.
Yeah.
All the graphs you've shown have high degrees of symmetry. Did you try reducing your search space by assuming the symmetry?
So we did try a little bit. I should say I don't really care about this particular problem. I don't care about what the exact answer for 64 is. I just really like this problem because it's just such a good place to test different methods. So I agree that symmetry would be the obvious thing I should try if I really cared about answer of f at 64. It doesn't really matter to me so much. The method itself was much more important to me. Any more questions?
Sometimes these constructions look symmetric and then they're not quite symmetric in one point.
Yeah, I think this is doesn't have 4-fold symmetry.
But it really looks like it would just scan the X, somehow it doesn't seem to put anything in the middle.
So that I can explain because the points in the middle are in many more isosceles triangles than.
Yes, but I mean, in this way, you could reduce the
Oh,
surface
yeah.
space from X squared to.
I absolutely agree. So if you cared about this particular value, you should do all of these things.
So the thing is that probably, you could do that, but Pegmore is going to do it for you. You feed it with examples that have nothing in the middle. So there's no way it will ever learn to generate something with anything in the middle. So yes, you could curate the data sets, but you don't need to.
Yeah,
So
I mean,
it's
in
already
the
in Moll's weight.
I meant in the local search, or maybe in the local search, you're not even trying to.
Yeah, true. You could improve the local search this way. But the transformer part.
Yeah, no, I wasn't thinking about the transform part, or even if you had an RL agent, your actions would only be to add on the other side.
You can definitely speed up the local search by doing this, and then you could do more local search. And there's lots and lots of improvements that are specific to this problem that you could definitely use. What I was, sorry. So what I was excited about here is that this method seemed to be a method that could be applied to many other problems as well. But this works for 64 by 64. Maybe we were lucky. Let's try it for 100 by 100. Of course, 100 by 100, we have no chance of finding optimal anymore. Let's just see what we can find. So we tried our standard methods for a couple of weeks, and the best we could find was 154. Once again, we saved the million best constructions. We gave it to make more. We asked it to generate new examples like these that I just showed them, and launched a tiny, tiny local search from each new construction generated by the transformer. And this immediately went up to 160. So the way I think of it is adding this tiny, tiny ML part on top of it gives you a way to improve any kind of local search algorithm. How much, whether you improve by epsilon or more, that depends on the problem. So here's the 154 that we found by standard methods, and here is the 160 that we found by putting this tiny amount of machine learning on top of it. Okay, so how do I think about this method? And I know that both Jordi and Juanza think about this very, very differently. So this is just my perspective on this method. The way I think about this is a transformer looks at a huge database and finds something in common between all these good constructions. So it's responsible for some kind of global picture that we're aiming for. And on top of that, we put this local search, that's of course responsible for fixing things locally. And somehow alternating these two things is better than the previous methods that we tried. I do want to mention that this is definitely not the first idea you would have if you're thinking of local global method, and it's definitely not the first algorithm we tried either. The thing with this this kind of machine learning problems is that, and it's something that drives me as a mathematician absolutely crazy, is that many times you dream up a beautiful algorithm that you're convinced it has to work very well, and then you try it and it just absolutely doesn't work at all. This is the algorithm that worked the best, not just for this problem, but also on many, many other problems. So in the end, what matters is how useful these algorithms are in practice. The algorithm I'm just presenting to you right now was by far the most useful thing that we found just by trying many algorithms that go into this local global direction. So in practice, just one more thing is that you iterate this process many times. So you do local search, build up a big database, we train on it, you generate new examples with a transformer, put a local search on top of it to end up with a new database, plug it back into the transformer, and we iterate it a couple of times, and that seems to be the best thing to do. So what I want to do in the next 5 minutes, I want to show you just very briefly a couple other problems on which this method was useful on, and I'm not going to go deeply into that. I just want to give you the melody to show you what kind of problems this method seemed to perform pretty well. So the first type of problems is problems with set systems. It seems that for several such problems, things work very well with this method. So here's the first one. Imagine you have a set of size n, and you keep picking subsets of this set, and you place them in front of you. The only one rule is that you're never allowed to have k sets where k is some fixed constant. You're not ever allowed to have k sets in front of you that form a chain. So the first one is a subset of the second one is a subset of the third one, and so on. So you keep choosing sets without violating this condition until you get stuck. The question is, what's the earliest time you can get stuck in this game? So this is now a question completely open. If you think about it for 5 minutes, you realize that it's very easy to get stuck after 2 to the k steps, but there's a very nice breakthrough result a couple of years ago where Morrison and Scott showed that you can actually do exponentially better. You can get stuck in exponentially less than 2 to the k steps. They also had a certain kind of epsilon that comes out from their construction. The good thing about this problem is that it boils down to constructing finite constructions, and you can calculate the epsilon from that. And if you find some better constructions, you get a better epsilon. So this problem is a perfect fit for our method. You can cook up a reward function. And if you apply this kind of transformer loop a couple of times, this epsilon starts improving, and we manage to get up to something like 0.04. Here's another type of very similar problem, also about set systems. Here we are trying to build multiple collections of sets. Once again, we have a certain kind of rule. The rule here is that you're never allowed to have two sets that are subsets of each other, and one of them is in one of the families, the other one is in another family. And the question is, how big can the volume of this collection of sets be? So how big can the product of all these set systems be? Once again, you can imagine, you can just write down some kind of reward function here. There's no obviously correct way to do it because you want to somehow maximize this product, but you want to take into account that you have some restrictions. You want to cook up some kind of penalty function. But if you do that, you end up improving constructions for many, many small values of answer k. Maybe 2 more examples. One is with percolation. So this is joint work with Gary Berti. So imagine you have the hypercube, so O01 sequence of n, and you infect some of the vertices of this hypercube initially. And then what happens is every single vertex looks around, and if they see at least R infected vertices in their neighborhood, also become infected. And then in the next round, every vertex looks around again, and now even more vertices get infected, and so on and so forth. Once a vertex is infected, it stays infected forever. Question is, what's the smallest size of initially infected vertices we can start with that will eventually affect everything. So this problem has a lot of literature. The best construction is due to Polybash and Morris, who noticed that you can do something very simple. You can take all points which have r-2 bonds in them, and you can do something smart on the set of points which have r bonds in them. This works. And by doing this method, we managed to improve this for all r at least 4. So here the transformer helped improving the constructions for large values of n. But to get this improvements, what we had to do is we had to actually understand the constructions. And the problem is that transformers helped in the large n case, but we couldn't understand those constructions. So to get this method, we actually didn't end up using transformers. If we were smarter, then we could probably understand the constructions that the transformers gave us for larger base, and we could get even bigger improvement. But to just beat the previous result, we didn't actually have to use these transformers at all. And maybe if I have 1 more minute, just one more example then. This is about boxes. So imagine you have the box 0, 1 to the d, and you want to partition it into sub-boxes. And the sub-box is just a direct product of d different sets. Only restriction is none of these b sub i's is the entire interval from 0 to 1. Question is, what's the fewest number of sub-boxes you can partition a box into? This has an equivalent phrasing in terms of tensors. You want to start with the all ones tensor, dimension d, with some big side length, and you want to write it as a sum of as few rank 1 tensors consisting of zeros and ones as possible. So what's the smallest number we can get away with? Does anyone have a guess, maybe? What would be a good construction here?
We get some conjectural in zero.
Sorry?
I think there's some conjectural in zero, right?
Yes.
It was 2 to the d, right?
Yeah, that's right, yeah. So with 2 to the d, it's very easy to do it. Just cut each direction in 2 pieces and take all possible direct products. And it turns out there's actually no better way to do it. And by the way, this is one of my favorite theorems in combinatorics. It's a beautiful theorem that has proof that's about 2 lines long. But coming up with this proof is, if you do it, I will be very impressed. It's an absolutely beautiful 2-line proof, but I don't think I was ever come up with it. So I challenge you, try to prove it if you can. Now, this problem is solved, but there are many, many variants of this that are completely open. For example, what about covering every single point of a box exactly twice? So you can observe that you can do it with less than 2 times 2 to the d. And there's a really nice question by Imre Lieder, the combinatorial question 10. He asked, is it possible that covering every point twice is easier than covering every point exactly once? It would be very, very surprising if the answer to this was yes. But it seems that maybe this is actually the case. And with this method, we managed to push this down all the way to 1.28 times 2 to the d. So we're getting very, very close to breaking the 2 to the d barrier, but we're not quite there yet. So this was just another problem where you can imagine you start with a couple of boxes, and then you have to measure how close is this collection of boxes to covering every point exactly twice, and cook up a reward function along these lines. And you can optimize this with the methods I just described. Okay, and I'm just going to wrap up now. I just want to say that I showed you a couple of methods that you can use on a wide range of problems. It's definitely not the case that these methods work on most problems. In fact, the opposite. On most problems, if you try to use methods, it's just not going to work very well, but they do seem to work on many, many problems. The most important thing is that it's very clear that things are still changing very quickly, and there's lots of low-hanging fruits. And I'm really, really excited to see what you guys will all come up with in the next few years. So I'm going to stop here, and thank you very much for listening.